In previous lecture, and we talked about connected components within a graph. And remember that just in simple terms, a connected component is a subgraph within a larger graph that is completely connected but isn't connected to the rest of the graph. For example, the upper component here and the lower component here are both subgraphs of the larger graph made up of all 7 vertices and their associated edges. Now, one thing I want you to notice before we start talking about matrices again is that I've numbered the vertices carefully so that each connected component has a sequential set of indices. The upper block has vertices 1 through 4, and the lower block has vertices 5 through 7. Now, before we move on, and I show you the adjacency matrix, this would be a good opportunity for you to pause the presentation and get a little practice in by writing it out yourself. Okay, so this is my result. And the interesting thing about this is what you can kind of visually pick out, right? Visually, you can see the 2 connected components within the matrix. This block has all the connections within the first component, the one in the upper left. And since there aren't any connections to the second one, that is to any vertices whose index is greater than 4, the remainder of these rows is completely filled in with zeros. And similarly, if you look at the bottom section, this 3 by 3 block has all the connections between the vertices of the second components, vertices 5 through 7, where this block to the left, the one for, in these rows for column indices 1 through 4, that is vertices with indices 1 through 4, also is a block of all zeros. So you can see in this example a general rule that a graph with connected components whose vertices are appropriately numbered is made up of rectangular blocks of zeros and rectangular blocks of non-zero values. So this theorem here formalizes what we saw on the previous slide. And really, hopefully you've got the idea with these blocks of zeros. But I did want to include this just so you can kind of see the language used, right? If we let G be a graph and it has K connected components, G1 through GK, and the vertices are numbered, right, in that sequential fashion that we saw in the previous slide, then the adjacency matrix has this form. It's made up of these big blocks of zeros. That's what the O's represent, right? That's a rectangular block whose values are all 0. And down along that main diagonal, you have the adjacency matrices for the individual connected components, right? So this is just kind of how we would say that if we wanted to write it out in a more formal way. I'm not going to go through all the steps of proving this. I kind of encourage you to do it yourself. I walked through the reasoning on the previous slide, so hopefully you can see what's going on here. So with this theorem, we saw a way to kind of get information from the visual layout of an adjacency matrix. I want to show one more application of these matrices. It's a really cool one, I think. It's one of the more interesting theorems and one of the more interesting proofs in the whole class. But to do that, you have to know how to multiply 2 matrices together. So in the next lecture, we're going to take a brief diversion, talk about how to do that. Then in the one after that, we'll circle back around and take a look at that application.